Hi everyone, welcome back. In this video I'm going to show you how to find the net force of a system that has more than one force, and more particularly that it has an angle in those forces. So in other words, I know this is a little blurry here, but I have two forces acting on some object right here. So remember, forces act as a pull, right? So one object being pulled this way, and one is going to be pulled that way. And the question is, if I were to summarize these forces, like the sum of the forces, how would they work? Now I can't just say, 5 newtons plus 8 newtons is the sum of the forces, 13 newtons. Now the reason why I can't do that is because forces are directional. So I have sum of the force. This is actually the 8 Newton force. Like I said, I know it's a little blurry here. And this is the 5 Newton force. So I hope you notice that adding these together don't give the value of the force, because some of the upward force will cancel some of the downward part of this force and vice versa. So this doesn't actually model the situation. So essentially what we're doing is called adding vectors together. So what we need to do is we need to find the vector components of the forces, add those together, and then recombine them and figure out the direction of the net force. So essentially, hold on one sec. Okay, so what I did actually is just pause a quick second to show you what we're going to be doing mathematically. So imagine you have two forces, alright? So I know they're not acting on the same object at the moment. But one way we can analyze two forces is by drawing the tip-to-tail method. So you can see I have the tail right here, and this is the tip. So what we're going to be doing, although this is a slightly different problem, is we're going to find what is called the average of the force, or the sum of the forces. So notice that the dotted line kind of represents the two arrows if we added them together. We can see that both of those arrows are going to the right, and they're both moving upward. So if we combine their upward and their rightward, we get the dotted line. So essentially what we're going to do is we're going to find the right and the upward, force vectors of the first one, and then the second one. And if you notice, if I just move these down, just like that, the dotted line that was the sum of the forces is the hypotenuse of the component addition of each of the forces. So notice if I added the x's together and the y's together, I get the same dotted line as what we drew earlier right here, the sum of the forces. So that's the theory of what we're going to be doing. So we're going to find the x and y, we're going to add them together and solve for the hypotenuse, which models the net force on the system. So that's the theory of what we're doing. So let me take you back now. I'm going to get out of this slideshow and go into this. There we go. Okay, so now we're back to the problem. So we're going to find the net force on this system right here. So what is the net force? So the question is, where is the dotted line that describes the two forces like this? So what I did there is just drew a guess, really. I'm going to solve for it, officially, but if you notice, some of this force is moving down and some of this force is moving up. So the net force is probably going to be less than this force right here. And you can see that they're both moving right, so the right components are going to add up to something longer like this. That is my prediction. Let's see if I'm correct. So I'm going to go ahead and just erase this for now. So what I'm going to do, and this is what you'll do in your lab, is take the force out of the problem. So I'm going to start off with this 8 Newton force right here. And what I have is going to be the x component and the y component, like that. Now I like to draw the arrows because it helps me get the sign. So this is according to the diagram labeled as F2. So this will be F2x for the component x and F2y, the component y. And we have the angle of this force with respect to the horizontal is 60 degrees right there. So I got to figure out these values. So what I'm going to do is take the hypotenuse times sine of 60, because we are opposite the 60, which gives us a sine, and we're next to, so that's going to yield a cosine, like that. So I'm going to go ahead and do that on my calculator. So 8 times sine 60, and I'm in degree mode, just checking here, 6.92. That'll be in newtons, and now I'll do the other one. 8 times cosine 60 is 4. So I quickly just do a sign check here. So this one's going to the right and this one's up. So this one is positive because it's up and positive because it's going right. And I'm getting it from the direction of my arrows. And notice that the sum of my arrows represent the motion, so it's going to the right and up. So notice that the arrow is to the right and up. Now again, I always emphasize that while teaching, you don't have to do this while you actually solve it out. So next what I'm going to do is take the 5 Newton one and draw it outside the problem, so it looks like this. This is labeled as F1 in the problem right here. And the angle that it makes up here is 20 degrees. So if I continue this for the horizontal piece, that will look like this to the right, and then my vertical piece will be down. Now you can, side note, don't copy this down, you could actually say alternate interior angles, then do it this way too. As long as you model the arrows correctly, that's fine, it doesn't matter. You can do that, but just for sake of doing this, let's go ahead and finish this up. I don't know what that just clicked on, okay. Okay. So actually, what I'm going to do, just because it's in my way, I'm just going to move this outside the triangle. So 5 newtons is the hypotenuse of F1. So this will be F1x, and this is F1y. And just because I'm running out of room, I'll just write them down here. So F1x, I should write the same way. F1x, there we go, is going to be 5 newtons, since it's next to, times cosine 20 degrees. And this will be a y, so 5 newtons sine 20 degrees. Go ahead and solve those out. So 5 times sine 20 gives 1.71 newtons, like that. And this one, 5 times cosine 20, gives me 4.698. I'm going to go 4.7 here, just around. Okay. So now what I'm going to do is, like I said, check signs. I see that fx goes to the right, so that's going to be positive, but notice that fy is down, so that will be a negative value. Now, some of you might use negative 20 here. It actually will work out if you do that, but I just like applying the signs at the end. I think it's just easier that way. Okay, so now that we have this, what we're going to do is we're going to add up the components. So I guess I should just quickly recap what we're doing. So the first thing you're going to do is you'll take out the force to find the x and y components of each force. Okay. So, and then of course taking note of signs, noting signs, signs of forces. So the next thing I'm going to do is now I'm going to add x components to get x total. And then I'm going to add y. So I'm not adding them together, I'm adding them separate because they are separate directions, so I must do them separately. So that's my next step, so I'm going to go ahead and do it. So my x total is going to be those values. So it's basically the F2 of x plus F1 of x. So F2 of x is positive 4 newtons plus positive 4.7 newtons, which gives me positive 8.7 newtons. Okay, and then we're going to do the same thing here. Alright, so the y component of the first one was 6.92 positive, okay. Plus, this one is negative. So, even though I'm adding them, yes, you can do 6.92 minus 1.71. That's totally fine. But I want to show you that I am adding them up. So, some of the negative force here is going to counter, right, the positive. So, it's less force in this direction. There we go. Fix this. So, when I did this, I get 5.21. And again, I like to emphasize the sign here, so the answer is still positive. So what am I going to do now? So what I'm going to do now is essentially find, now that I have my coordinates of my system, I'm going to find the net force by making a triangle with my component forces and solving for the hypotenuse. Which represents the net force. Okay, so in other words, what we're going to do is we're going to take our x total, whatever that value is. We're going to put the y total at the end of the x total. So it doesn't always look like this and in this direction. I'm just choosing this right now. And this right here will represent the net force of the system. So we basically are going to solve this triangle completely. So I'm just going to redraw it because this is what I'm doing, but now I'm going to use use the actual numbers to show you here. So my first x total was 8.7, right? So x total is 8.7, so I'm going to go ahead and draw that. And it's positive, so I'll do 8.7 like this, which means positive means to the right, so 8.7 newtons. And then my y is positive 5.2, so I'm just reading it out off my calculator. So it goes up a little less than the 8, so 5.2 newtons. So essentially I'm solving for this, which I will call the net force. So the best way to solve for this without an angle is the Pythagorean theorem. So sorry about that. Let's go down. So I like to do the Pythagorean theorem in one step, but note you are in fact doing it. So if I take the square root of the squares of the sides of the triangle, we can do the Pythagorean theorem in one step. So 8.7 squared plus 5.21 squared, then I square root that value. Perfect. 10.14 newtons. So that's the magnitude right here of our force, so how strong it is right there. But we also like to know where it's pointing, so the angle is important too. So find the angle, right? So the angle of that force can be solved with any of the values here because you have all the legs of the triangle. But as you already know, my personal favorite in one step is the inverse tan of y over x. Sorry, I'll try to make that more y-like. So if I do that, it's going to be the y, which is the 5.21 newtons, divided by the x. So 5.21 divided by 8.7 inverse tan of the angle. The angle is 30.91 degrees, like that. Okay, so what did we actually solve for, right? So if I go back to our drawing here, basically, if I were to combine these two forces right here, it'd be like a force that is moving, it has an angle of 30 degrees. So let me try to model that as best as I can. So 30 is about, oh, that's still too high. Too high. A little less than that. A little more than 20. Good enough. I don't think that's good, but that's okay. So this would be 30.91 degrees. That's what this number represents of this coordinate system. And the value would be 10.15 newtons. So this is the net force of the system right here. So instead of drawing two forces, we can model the whole system as just one force here. And that's how you can find the net force. Now, if I had a third force, I would just do another triangle. So that's how you approach, if I had 4 forces, 5 forces, you just add to this. And what happens is these just become longer. It's just x1, x2, x3, x4, so however many forces that you have. Also, if you want to balance this force, right, like you might do in lab, big hint, to balance that force, or those two forces, you need to find the net force. So let me just make a comment on that. So in lab, you're going to balance the force, and the way you're going to do that is you need to first find the net force, which is kind of what we did. So just quickly, we had an 8 Newton force like this, and then we had a 2 Newton force like this. Of course, there's angles and stuff like that. So what we did is actually found the net force, which looks more like this, of 10.14, like that. Well, if I find the net force, in order to balance, I must have the same magnitude. But notice, I have to cancel out both x and y. So that means that the angle will be the same here and here, using alternate interior angles. So if this is 30.91 degrees, this must be 30.91 degrees. Because my x force, the x component over here, must cancel the x component here. And vice versa. The down component must cancel the up component. So in lab, you're going to do this. You'll find the net force and then determine where to put the other force so that the whole system actually balances out. It's a really cool lab that you can do here. So in essence, that's how you find a net force of a system that has more than one type of force.